This PowerPoint is over magnetism. A compass, the purpose of a compass is in order to line up with a magnetic field. It's a tool used in order to determine the magnetic field around a bar magnet. Here we see the compass is actually pointing away. The red end is the direction of the magnetic field, so it points away from a north and toward a south. And that's actually what happens with a compass. It always points towards a south magnetic pole. It always lines up with a magnetic field in pointing away from the north and toward the south. Now, permanent magnets have permanent magnetic fields around them, and you can see that with a magnetic field here. We have the compass that's lining up with it. At any given point, the compass will line up with it, but the total map of the area, what happens to the magnetic field is it goes out, and then the magnetic field is concentrated at these 2 points right here as the magnetic field comes into the south and out of the north. And we got that concentration. Over here we see a bar magnet with some iron filings around it. Now, there's nothing in nature that says that the magnetic field has to come out of a north and into the south, but that's just something that scientists have set up as a convention so that, you know, when we start talking about the direction of the magnetic field, we can be consistent when talking to other people. So these iron filings, they're little pieces of iron. They act like compasses essentially, and they line up with the magnetic field. And you can see here with the map, you can see that the iron filings line up, so the lines go from north to south. So a permanent magnet is a fixed magnet. It's a magnet that has a magnetic field with a definite north and south pole. So we have two magnets here that both have north, north, and we got south, south. And we know that those are going to repel because like poles are going to repel. But if we take these two magnets right here and put them close to each other, we see that the north and south are going to attract. So the north, north repels, south, south repels, but the north and south are going to attract. The magnetic poles, they're not separate poles. If we break this magnet into two pieces, we don't get a south pole over here and a north pole over there. We actually get two separate magnets. We get a south and a north, and then a south and a north. And the reason we know we get two separate magnets is because if I take this part right here and flip it around backwards, I'm going to have two souths, and they actually repel from each other as opposed to attracting. If they were both just separate poles, then they would always attract to each other. But I know if I flip one around, it'll repel as well. Now, the reason for that is because these magnets are not just one magnet. What they are is they're billions and billions of little magnets, and each atom is actually its own magnet. There are three elements that are naturally magnetic. That's iron, cobalt, and nickel. And when those three elements are present, they're going to form what's referred to as magnetic domains. And each one of those atoms has a magnetic domain, which basically means that it points in a certain direction with a north magnetic field pointing out of the north. When all of those domains are aligned in the same direction, you get your permanent magnet. When they're all going in every which direction, it still has magnetic properties, but it's not a magnet. A ferromagnetic material is actually a material that has magnetic domains in it, but it's not ordinarily magnetic because those magnetic domains are just every which direction. But it will become magnetic. They will start to align. They won't align perfectly, but they will all start to kind of point in the same direction if you have a magnetic field around it. So if I have a permanent magnet here with a north end and a south end, and let's say this is a ferromagnetic material, an example of this would be like a nail that you would drive into something. We have this end that's going to attract to it, it's going to be the south end, and then the other end is going to be the north end. If we actually take this nail, this ferromagnetic material, and unattach it and turn it around, it'll attract again because the magnetic domains will line up so that they attract, and they always point in the same direction as the magnetic field of the permanent magnet. So it'll always be attractive. Earth's magnetic field, consequently, with Earth's magnetic field, if we say that the compass always points toward a south magnetic pole, we know the compass always points geographically north. Now, the fact that it points geographically north has really nothing to do with the compass as much as because there's a south magnetic pole near the north geographic pole. Now, why is it that there's a south magnetic pole near the north geographic pole? Well, it comes back when navigators from far back had compasses, and what they did is with that compass they would say, well, here, this end of the compass points north, so I'm going to call that end of the compass north. Well, the problem with that is if you say, well, that end of the compass is north, it's got to be attracting toward a south pole. So even though it's pointing north, they have consequently basically said with that end of the compass being north that it's pointing towards a south magnetic pole. So there is a south magnetic pole where close to where the north geographic pole is. And this pole actually switches around a little bit. It actually moves a couple miles and it stays in the general same location but it does move around some. Now, we've known that the magnetic field of the Earth has actually switched. It's actually flipped many times throughout the history of the Earth. And the reason we know that is because right down the middle of the mid-oceanic ridge, there is basically this ridge of two diverging plates, where plates are separating from each other, and in that gap there's material, lava and magma that comes up, and it solidifies in the middle. Well, inside of that material, there are a bunch of magnetic domains, and when the material is liquid, those magnetic domains can go every which direction. So when that material comes up to the surface, it aligns with Earth's magnetic field and points in a certain direction. Then when it becomes solid, those magnetic domains are stuck in place. Well, if you start at the mid-oceanic ridge and move outward from there, you see that there are some magnetic properties that point in one direction. As you move further away, it points in the opposite direction. And that's how we know that the magnetic field has changed, because those magnetic domains are pointing one way, and then maybe several miles later they'll point the opposite direction. Then several miles later they'll point back the same direction as it was before. And we can see that magnetic domains are switching, which means the magnetic field of the Earth was switching as well. So a few things that we can use magnets for storing information. Computer hard drives store information. Essentially what a computer hard drive is, it's a big long strip of magnets, and all those magnets are facing in the same direction until it's formatted. Now when those magnets are formatted, they're changed so that you have either a north pointed up, which can be identified as a 1, or a north pointed down, which can be identified as a 0. So if you take those magnets, and essentially you got 8 of them in a row, those little magnets are referred to as bits, and then 8 of those is referred to as a byte. So a byte of information, and I believe there's about 256 different combinations you can have those facing up or down, 1, 1, 0, or whatever combination you can have. Making electricity, we know that magnetism, actually a changing magnetic field around a wire, can create electricity in that wire, and that's actually something we're going to be looking at later. Additionally, navigation, obviously with the compass, it points towards the north geographic pole, not because it's a north geographic pole, because there exists a south magnetic pole near it. And then lastly, it picks up hard to reach items. We're able to use ferromagnetic material inside of objects that we may misplace, or may drop behind a tool table or something like that, and be able to use a magnet in order to pick them up.